Matrices going okay for everybody. Looking like most everybody's keeping up pretty well. Grades are looking pretty nice in here. I don't think anyone is required to be here on Thursday for RTI, if I remember correctly. Let me double check that since I said that. Log into that real quick. Fifth period. No, there's nobody scheduled to be here in RTI Thursday because everybody's grade is doing well. Nobody's below 70. Man, most of the class isn't even close to 70. I don't know that anybody's worried about dropping below 70. Because you guys are doing very, very well. That's that's not uncommon with the Algebra 3 folks. By this point, you guys have got school figured out. You can only do really well in this class, and I don't have to worry about anyone getting too far behind or failing or anything like that in Algebra 3. I can't remember the last time I had someone fail a semester of Algebra 3. Because you guys rock. All right. We're still missing like 10 people, though, at the moment. We'll give it another minute or two. I don't think we're that pressed for time today. We got a few lessons to go through, but most of them are videos today. Or all of them are videos today, it looks like. But we got to do some stuff on inverses of matrices today and a determinant. Like, that's a new word, determinant of a matrix. So we're going to learn how to do the determinant of a 2 by 2. Bigger ones are a lot more work. We're not going to work with solving bigger than a 2 by 2, but it can be done. So we will get there. So, all right. Well, it's almost 9 o'clock, so I've given almost an extra 5 minutes in here. We'll go ahead and get started, and everybody else will just have to catch us on the fly. We're already running down the road. They'll have to jump on the bus while it's moving. Looking at our grade screen. Wait, did not go to the grade screen. It went down here. That's weird. Look at our grade screen. There we go. Okay, we did the sequences and series. Here's all the matrix work we've done, and there's been quite a bit of it. So you should have everything turned in through quiz 2. This week we'll have quiz 3. So we've got to do the assignments that come before quiz 3. And then next week we'll finish up. Not next week. Next week's spring break. We ain't doing nothing. When we get back from spring break, we'll finish up matrices and finish this last part of it. But we are going to do, let's see, March 22nd, determinant and the inverses. So we'll do both of those folders, the determinant of a 2 by 2 matrix and introduction to matrix inverses and quiz 3. So that's what we have this week. Let's go back to activities, scroll down. Properties of matrix multiplication. We've done that. Close that folder. Right here, right before quiz 3. So we have 2 folders in quiz 3 to look at. Well, let's pull it up here. Determinant of a 2 by 2 matrix video lesson. On that, let's see what what's his name, Saul, I think, something like that. See what he has to say about a determinant here.
As a hint, I'll take the determinant of a very similar 2 by 2 matrix. So we want to figure out the determinant of this matrix, and we can denote it by the determinant of the 2 by 2 matrix 5, 3, -1, and 4. And the definition of a determinant of a 2 by 2 matrix like this is we can first take this diagonal, 5 times 4. So let me write that down. So it's going to be 5, it's going to be equal to 5 times 4 minus the product of this diagonal, minus the product of that diagonal. So minus 3 times -1. 3 times -1. So what does this give us? So 5 times 4 is 20. And then 3 times negative 1 would be negative 3. This is negative 3. But then we're subtracting negative 3, which would make it adding a positive 3. So 20 plus 3. And so the determinant of this matrix, ready for the drum roll, is 20 plus 3 is 23.
So the determinant is just a number that you get.
23
Yep. Stop. Pause. I was trying to get to pause.
is
There we go. And the way it's calculated is we take the top left and bottom right numbers, multiplies together, and then subtract what the other two numbers multiplied together is. So we're going to practice this. We'll get off the screen. So that's a very quick video. Didn't take very long at all. Let's look at the assignment where we're going to practice this. Of course, we're going to take the screenshot, put it down at the bottom. So let's do some practice with determining the determinant. Determining the determinant. That's an interesting way to say that. Okay, so if we have this, and I'm going to give us some practice on this because this is something a little different. We only do determinants when we deal with matrices. So let's do it like this. So you said the way to determine determinant is we'll take those two numbers and multiply them together. 1 times 5. So that's 5. And then we'll subtract these other two numbers right here. Multiplied together. So we'll subtract 0 times negative 1. So we'll subtract 0. So the determinant of this matrix, this 2 by 2 matrix, is just 5. That's simple. So 5. That's simple. All right, let's try another one. Negative 2 times 1 is negative 2. Minus negative 1 times negative 2 is a positive 2, right? Because a negative times negative is a positive. So we have negative 2 minus 2. Negative 4, right? Negative 2 minus 2 more. All right, I'm going to let you do the next one. So get ready to put this next one in the chat. We have the 2 by 2 matrix of 5, 3, negative 2, and 1. Make it a little bigger. I think you can see that pretty clearly. What would the determinant be of this matrix? And again, there is a way to do determinants of larger matrices, but we're just going to stop at 2 by 2s. You do this in college, you can get to the bigger ones. All right, I'm seeing some answers pop up in the chat. Remember, you are... Oh, I was not meaning to click over there. We're taking those two numbers, multiplying them together, subtracting these two numbers multiplied together. So yes, 5 times 1 is 5, minus, and negative 2 times 3 is a negative 6. So 5 minus negative 6 should be 11. Good work. All right, let's do the last one. What would the determinant be of C? Determinant of C. 0 times 2 minus, so this is 0, right? Minus negative 2 times 1. Negative 2 times 1. So minus negative 2. So 0 minus -2. Subtracting a negative means to add, right? So let's see how we did. Perfect. All right, let's take a screenshot to turn that in. Oh, I didn't take my summary. Hold on. That's what I want the screenshot of. Okay, screenshot of the summary. Oh, I got the confetti. I got the confetti in there. Yay, I like catching the confetti. All right, let's go back here. Turn in our screenshot with all our confetti showing. And submit. So the determinant of a 2 by 2 is not bad. Just as long as you keep your negative numbers straight. Sometimes you're subtracting a negative. As long as you don't forget that, I don't think you'll have any trouble with the determinant of a 2 by 2 matrix. So that was real easy. Let's close that folder. Now we have the introduction to inverses. Inverses. And this is where the determinant is going to help us because we have to use the determinant when we work with inverses. So let's check out this one. Looks like this can be pretty short this week. We just have 3 video lessons and 3, and then the quiz, of course. So let's see how long this one is.
We've learned about matrix addition, matrix subtraction, matrix multiplication, so you might be wondering, is there the equivalent of matrix division? And before we get into that, well, let me introduce some concepts to you, and then we'll see that there is something that maybe isn't exactly division, but it's analogous to it. So before we introduce that, I'm going to introduce you to the concept of an identity matrix. So an identity matrix is a matrix, and I'll denote that by capital I. When I multiply it times another matrix, actually, I don't know if I should write that dot there. But anyway, when I multiply it times another matrix, I get that other matrix. Or when I multiply that matrix times the identity matrix, I get the matrix again. And it's important to realize when we're doing matrix multiplication that direction matters. So it's actually, I've actually given you some information here that we can't just assume when we were doing regular multiplication that, A times B is always equal to B times A. It's important when we're doing matrix multiplication to kind of confirm that it matters what direction you do the multiplication in. But anyway, and actually I just want to make sure this works both ways only if we're dealing with square matrices. It can work in one direction or another if this matrix is non-square, but it won't work in both. And you can think about that just in terms of how we learned matrix multiplication, why that happens. But anyway, I've defined this matrix. Now what does this matrix actually look like? It's actually pretty simple. If we have a 2 by 2 matrix, the identity matrix is 1, 0, 0, 1. If you want 3 by 3, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. I think you see the pattern. If you want a 4 by 4, the identity matrix is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So you can see all the identity matrix is for a given dimension. I mean, we could extend this to an n by n matrix, is you just have ones along this top left to bottom right diagonals, and everything else is a 0. So I've told you that. Let's prove that it actually works. So let's take this matrix and multiply it times another matrix and confirm that that matrix doesn't change. So if we take 1, 0, 0, 1, and let's multiply it times, let's do a general matrix, just so you see that this works for all numbers, A, B, C, D. So what does that equal? So we're going to multiply this row times this column. 1 times A plus 0 times C is A. And that row times this column. 1 times B plus 0 times D, that's B. Then this row times this column. 0 times A plus 1 times C is C. And then finally this row times this column. 0 times B plus 1 times D, well, that's just D. And there you have it. And it might be a fun exercise to try it the other way around as well. And I think actually it's an even better exercise to try this with a 3 by 3. And you'll see it all works out. And a good exercise for you is to kind of think about why it works. And if you think about it, it's because You're getting your row information from here and your column information from here. And essentially, anytime you're multiplying, let's say, this vector times this vector, you're multiplying the corresponding terms and then adding them, right? So if you have a 1 and a 0, this 0 is going to cancel out anything but the first term in this column vector. So that's why you're just left with A. And that's why it's going to cancel out everything but the first term in this column vector. And that's why you're left with just B. And similarly, this will cancel out everything but the second term. So that's why you're left with just C there. Right? This times this, you're just left with C. This times this, you're just left with D. And that same thing applies when you go to 3 by 3 or n by n vectors. So that's interesting. You have the identity vector. Now, if we wanted to complete our analogy, so let's think about it. We know in regular mathematics, if I have 1 times A, I get A. And we also know that 1 over A times A, this is just regular math. This has nothing to do with matrices, is equal to 1. Right? So, and we call this the inverse of A. And that's also the same thing as dividing by the number A. Right? So is there a matrix analogy? Is there a matrix, and let me switch colors because I've used this green a little bit too much. Is there a matrix where if I have the matrix A and I multiply it by this matrix, and I'll call that the inverse of A, is there a matrix where I am left with not the number 1, but I'm left with kind of the 1 equivalent in the matrix world, where I'm left with the identity matrix? And it would be extra nice if I could actually switch this multiplication around. So A times A inverse should also be equal to the identity matrix. And if you think about it, if both of these things are true, then they're actually, not only is A inverse the inverse of A, but A is also the inverse of A inverse. So they're each other's inverses. That's that's all I meant to say. And it turns out there is such a matrix. It's called the inverse of A, as I've said 3 times already. And I will now show you how to calculate it. So let's do that. And we'll see calculating it for a 2 by 2 is fairly straightforward, although you might think it's a little mysterious as to how people came up with the mechanics of it or the algorithm for it. 3 by 3 becomes a little hairy. 4 by 4 will take you all day. 5 by 5, well, you're almost definitely going to do a careless mistake if you did the inverse of a 5 by 5 matrix, and that's better left to a computer. But anyway, how do we calculate the matrix? So let's do that, and then we'll confirm that it really is the inverse. So if I have a matrix A, and that is, let's just say A, B, C, D, and I want to calculate its inverse is actually, and this is going to seem like voodoo, and in the future videos, I will give you a little bit more intuition for why this works. I'll actually show you how this came about. But for now, it's almost better just to memorize the steps, just so you have the confidence that you know that you can calculate an inverse. It's equal to 1 over this number times this A times D minus B times C. A, D minus BC. And this quantity down here, AD minus BC, we'll learn soon, has a special, well, actually, we don't have to learn it soon. That's called the determinant of the matrix A. And we're going to multiply that. And so this is just a number, right? This is just a scalar quantity. And we're going to multiply that by, you switch the A and the D, you switch the top left and the bottom right. So you're left with D and A. And you make these two, you make the bottom left and the top right, you make them negative. So minus C and minus B. And the determinant, and once again, this is something that you're just going to have to take a little bit on faith right now. In future videos, I promise to give you more intuition. But it's actually kind of sophisticated to learn what the determinant is. And if you're doing this in your high school class, you kind of just have to know how to calculate it, although I don't like telling you that. So what is this? So this is also called the determinant of A. So you might see on an exam, figure out the determinant of A. So that, let me just tell you that. And that's denoted by A and kind of absolute value signs. And that's equal to AD minus BC. So another way of saying this could be 1 over the determinant. So you could write A inverse is equal to 1 over the determinant of A times D minus B minus C A. Any way you look at it. But let's apply this to a real problem, and you'll see that it's actually not so bad. So let's say that I have a matrix. Well, let's change letters, just so you know that it doesn't always have to be an A. Let's say I have a matrix B. And the matrix B is 3, I'm just going to pick random numbers, minus 4, 2, minus 5. Let's calculate B inverse. So B inverse is going to be equal 1 over the determinant of B. Well, what's the determinant? It's 3 times minus 5 minus 2 times minus 4. So 3 times minus 5 is minus 15. Minus 2 times minus 4. So 2 times minus 4 is minus 8, but we're going to subtract that. So it's plus 8. Plus 8. And we're going to multiply that times what? Well, we switch these two terms, so it's minus 5 and 3, and we just make these two terms negative. Minus 2 and 4, right? 4 is minus 4, so now it becomes 4. And let's see if we can simplify this a little bit. So B inverse is equal to, it's minus 15 plus 8, that's minus 7. So this is minus 1/7. So the determinant of B, we could write B's determinant is equal to minus 7. So it's minus 1/7 times minus 5, 4, minus 2, 3, which is equal to, this is just a scalar, this is just a number, so we multiply it times each of the elements. So that is equal to minus, minus, plus. So it's 5/7. 5/7 minus 4/7. See, positive 2/7, 2/7, and then minus 3/7. Minus 3/7. It's a little hairy. We ended up with fractions in here and things. But let's confirm that this really is the inverse of the matrix B. Let's multiply them out. So before I do that, I should create some space. Let me create some space here. I don't even need this anymore. There you go. Okay, so let's confirm that that times this, or this times that, is really equal to the identity matrix. So let's do that. So let me switch colors. So B inverse is 5/7, if I haven't made any careless mistakes, minus 4/7, 2/7, minus 3/7. That's B inverse, and let me multiply that by B. 3 minus 4, 2 minus 5. Now this is going to be the product matrix. I need some space to do my calculations. So let's see. First I'm going to take this, switch colors. I'm going to take this row times this column. So 5/7 times 3 is what? 15/7. 15/7 plus minus 4/7 times 2. So minus 4/7 times 2 is, it's minus, let me make sure that's right. 5 times 3 is 15/7. Minus 4, oh yeah, right. 4 times 2 is, so minus 8/7. Minus 8/7. Now we're going to multiply this row times this column. So 5 times minus 4 is minus 20/7. So minus 20/7 plus minus 4. Right, so minus 4/7 times minus 5, that is plus 20/7. Plus 20/7. My brain is starting to slow down, having to do matrix multiplications with fractions with negative numbers. But this is a good exercise for multiple parts of the brain. But anyway, so let's go down and do this term. So now we're going to multiply this row times this column. So 2/7 times 3 is 6/7 plus minus 3/7 times 2. So that's minus 6/7. One term left, home stretch. 2/7 times minus 4 is minus 8/7. Minus 8/7, right? 2/7 times 4 is minus 8/7 plus minus 3/7 times minus 5. So those negatives cancel out, and we're left with plus 15/7. 15/7. And if we simplify, what do we get? 15 sevenths minus 8 sevenths is 7 sevenths. Well, that's just 1. This is 0, clearly. This is 0. 6 sevenths minus 6 sevenths is 0. And then minus 8 sevenths plus 15 sevenths, that's 7 sevenths. That's 1 again. And there you have it. We have actually managed to inverse this matrix. And it actually, as you see, it was actually harder to prove that it was the inverse by multiplying it, just because we had to do all this fraction and negative number math. But hopefully that satisfies you, and you could try it the other way around to confirm that if you multiply it the other way, you'd also get the identity matrix. But anyway, that is how you calculate the inverse of a 2 by 2. And as we'll see in the next video, calculating by the inverse of a 3 by 3 matrix is even more fun. See you soon.
Well, it was a lot harder to prove that was the inverse than to find the inverse. But that is how inverse matrices work. Let's take a look at what our assignment looks like on this one then. So there's our screen. Let's see if we can find some inverse of some matrices, determining inverse matrix. All right. So it gives us this matrix right here, 3, 7, 2, 1. And this one, which is B, and it's these fractions, and it wants to know, are these inverses or not? Are these inverses? So here's how I'm going to determine that. I'm going to write these down, and we are going to do the multiplication to see if we end up with the identity matrix. So let me copy all these down. So I wrote down how the inverse works. One over the determinant, and then you switch the A and the D, and you just change the signs of the B and the C. So I've got that. You probably want that in your notes, that this is how you get the inverse. But to check to see if these are inverses, we multiply them together. So which means we have to start with the first row times the first column in matrix multiplication. So 3 times negative 1/11 is negative 3/11 plus 7 times 2. 7 times 2/11. So it's plus 14/11. Okay. Then we do times the second one. 3 times 7/11. So that's 21/11 plus 7 times negative 3/11. So that's subtracting then, since it's a negative plus a negative. So we're subtracting 3 times 7 is 21/11. Okay, now the same thing with the second row. 2 times negative 1/11 is negative 2/11. This is good practice on our fractions. And then 1 times 2/11. So add 2/11. 2 times 7/11 would be 14/11 plus 1 times negative 3. So we're subtracting negative 3/11. So let's simplify this. What does this equal? Negative 3/11 plus 14/11 is 11/11. That's 11/11, which is just 1. 21/11 minus 21/11 is 0. Negative 2/11 plus 2/11 is 0. 14/11 minus 3/11 is 11/11 again. This is the identity matrix. These are inverses of one another. The other way we could have done that is we could have just taken the matrix A and found the inverse of it, if we wanted to go through this process and see if the inverse was this. But since we had both of them, multiplying them together to find the inverse, to find the identity matrix, says, yes, these are inverses. Check. That is correct. So you can see this is going to be a little trickier. You really got to keep straight your fractions, which line you're on. Okay, here's our second problem. So if you have some pencil and paper there, I'm going to work this with my pencil and paper, but I'm not going to show you. I want you to come up with an answer and tell me, are they inverses or are they not inverses? And like I say, you can do it either way. You can either find the inverse of A and see if it equals B, or multiply them together. So I'm going to give you a moment to do that while I do that myself on paper and see what I come up with, and we'll see if that matches what you come up with. Takes a little while just to do one problem with these, doesn't it? All right, I've got an answer, but I'm gonna wait a minute. Just looking for a yes or no here. Are they inverses? Daniel's already got an answer as well. Peyton's got an answer. This was a little easier. The no is a little easier, and a lot of people get no. The no is a little easier than the yes because you don't actually have to finish. Don't actually have to finish. Here, I'll show you what I mean because people are saying no. Here's what I figured out. I wrote them down and I started multiplying the first row, the first test. So I did the first row. 4 times 326 is 1226 plus 7 times negative 113. So it's minus 713. Well, you have to have the same denominator in order to add or subtract fractions. Well, 1226 simplifies to 6/13. So they both are 13ths. And once I take 6/13 minus 7/13, I've got negative 1/13, which already tells me this is not the identity matrix. That has to be a 1. When this is not, I didn't even have to do this really. I was doing that before I started simplifying. But once this first number does not end up a 1, I'm done. It's not an identity matrix. So the trickiest part about this is just making sure you know how to subtract fractions. I could have doubled this to make this a 1426, but still that would be negative 226, which simplifies to negative 1/13. But either way, it's not 1. So that one wasn't too bad because we didn't have to do all of those fractions. We didn't have to finish it once we get to the first one and it doesn't work out right. We can come back and say, no, these are not inverse. Nice work. All right, next one. All right, try these two. And again, I'll work it on paper separately here. All right, I've got mine whenever I'll get a couple of minutes. Peyton's finished. It's okay if we're quicker. I went through that a little quick, so take your time. This has two different denominators, 3's and 9's, but fortunately, when you do the multiplication, you're only comparing thirds to thirds and ninths to ninths. So you don't have to convert any, simplify, subtract, or add. Okay, we've got a couple of folks that are finished. They have an answer. Okay, we have several people. I'm going to go ahead and put my work up on the screen now. So taking these two multiplied, I end up with 4/3 minus 1/3 as the first number in the matrix, which 4/3 minus 1/3 is 3/3, which is just 1. Then when you multiply the first row times the second column, you get negative 2/9 plus 2/9. Again, they're both ninths. That's nice. You don't have to do any conversions. And that's just 0/9, which is 0. Then with the second row first column, you got 6/3 minus 6/3, which is 0/3, which is a 0. And then second row times second column, negative 3/9 plus 12/9, negative 3 plus 12, 9/9, which is 1. So we end up with the identity matrix 1001. So all those folks that are putting a yes also got the identity matrix. Perfect. One to go. Oh, and this one's pretty tricky. It uses 71st. This is probably the first time in my life I've used a fraction that has 71 as the denominator. Kind of excited about that. All right, let's work one more. All right, take your time on that one. At least all the denominators are the same. So all we have to do is add or subtract the numerators and put them over 71. So not having to convert any denominators. So that does simplify it. It's just weird working with 71 in your fraction. I had to work through this one carefully because I almost made a mistake and I was putting it in the wrong places. But as you figure out your answer, put it in the chat. Yes or no? Are these inverses? Had to go back and double check they got the positives and the negatives in the right place. All right, we got several people got that one answered. Let me put up my work on the screen, see how yours compares. So negative 11 times a negative 7, 71st. So negative times a negative, that's actually a positive 77, 71st. And then negative 3 times 2 is negative 6. So 77 minus 6 is 71. So this is 71 over 71, which is just a 1. And then doing the first row in the second column, you got the negative times the negative again with negative 11 and negative 3. So that's a positive 33 71st. Then you got the negative 3 times the 11. Negative 3 times 11 is negative 33. So you got 33 71s minus 33 71s. So that's just a 0. Then you have to do, this is where I started to mess up. I started to do the second row, second column first, and I was getting this numbers. That can't be a 1. Then I realized I had skipped the first column. Negative 7 times 2 is negative 14 71s. 7 times 2 is a positive 14. So negative 14 plus 14 is 0 71s, 0. And then the negative 6 and the positive 77 make 71. So this is actually the inverse of the first matrix. Just had to be careful with all those big numbers. I was getting mixed up on my rows and columns, but it says yes, we are correct. Where's my screenshot? There it is. Oh, I missed all the confetti. That's all right. All right, let's go back here, scroll down, paste our confetti, submit my work. All right, we have determining invertible matrices, which makes you think, that means not all matrices have an inverse. So this is going to show us a method on how to know if you can even find the inverse, because it's not possible with all matrices.
Perhaps even more interesting than finding the inverse of a matrix is trying to determine when an inverse of a matrix doesn't exist or when it's undefined. And a matrix, a square matrix for which there is no inverse or for which an inverse is undefined, is called a singular matrix. So let's think about what a singular matrix will look like and how that applies to the different problems that we've addressed using matrices. So if I had and I'll do a 2 by 2 because that's just a simpler example, but it carries over into really any size square matrix. So let's take our 2 by 2 matrix, and the elements are A, B, C, and D. What's the inverse of that matrix? Well, this hopefully is a bit of second nature to you now. It's 1 over the determinant of A, 1 over the determinant of A, times the adjoint of A. And in this case, you just switch these two terms. So you have a D and an A, and you make these two terms negative. So you have minus C and minus B. So my question to you is, what will make this entire expression undefined? Well, it doesn't matter what numbers I have. If I have numbers here that make A defined, then I can obviously swap them or make them negative, and it won't change this part of the expression. But what would create a problem is if we attempted to divide by 0 here, if the determinant of the matrix A were undefined. So A inverse is undefined, if and only if, and in math they sometimes write it, if with two F's, if and only if the determinant of A is equal to 0. So another way to view that is, if a determinant of any matrix is equal to 0, then that matrix is a singular matrix and it has no inverse, or the inverse is undefined. So let's think about in conceptual terms, at least the two problems that we've looked at, what a zero determinant means, and see if we can get a little bit of intuition for why there is no inverse. So what is a zero determinant? Well, in this case, what's the determinant of this 2 by 2? Well, the determinant of A is equal to what? It's equal to AD minus BC. It's equal to AD minus BC. So this matrix is singular, or it has no inverse, if this expression is equal to 0. So let me write that over here. So if AD is equal to BC, or we can just manipulate things, and we could say if A over B is equal to C over D, right? I just divide both sides by B and divide both sides by D. So if the ratio of A to B is the same as the ratio of C to D, then this will have no inverse. Or another way, we could write this expression, if A over C, if I divide both sides by C and divide both sides by D, is equal to B over D. So another way that this would be singular is if, and it's actually the same way, if this is true, then this is true. These are the same, just a little bit of algebraic manipulation. But if the ratio of A to C is equal to the ratio of B to D, and you can think about why that's the same thing as the ratio of A to B being the same thing as the ratio of C to D. Anyway, I don't want to confuse you. But let's think about how that translates into some of the problems that we looked at. So let's say that we wanted to look at the problem. Let's say that we had this matrix representing the problem, the linear equation problem. Well, actually, this could be either one. So we have A, B, C, D times X, Y is equal to, I don't know, two other numbers that we haven't used yet, E and F. So if we have this matrix equation representing the linear equation problem, then the linear equation problem would be translated A times X plus B times Y plus B times Y is equal to E, and C times X plus D times Y is equal to F. And we would want to see where these two intersect. That would be the solution, the vector solution to this equation. And so just to get a visual understanding of what these two lines look like, let's put it into kind of the slope y-intercept form. So this would become what? In this case, y is equal to what? Y is equal to minus a over b minus a
over b x plus e over b, right? I'm just skipping some steps, but you subtract ax from both sides, and then divide both sides by b, and you get that. And then this equation, if you put it in the same form, just solve for y, you get y is equal to what? Minus c over d minus c over d x minus c over dx plus f over y. So let's think about this. I should probably change colors because it looks too. Let's think about these two equations. What these two equations would look like if this holds, right? And we said if this holds, then we have no determinant, and this becomes a singular matrix, and it has no inverse, and since it has no inverse, you can't solve this equation by multiplying both sides by the inverse, because the inverse doesn't exist. So let's think about this. If this is true, we have no determinant, but what does that mean intuitively in terms of these equations? Well, if a over b is equal to c over d, if a over b is equal to c over d, these two lines will have the same slope. They'll have the same slope. So if these two expressions are different, then what do we know about them? If two lines that have the same slope and different y-intercepts, they're parallel to each other, and they will never, ever intersect. So we could, let me draw that just so you get the. So if that's, so this top line might look, well, they both have, let's say these are, they don't have to be positive numbers, but this has a negative. I'll draw it as a negative slope. So that's the first line, and its y-intercept will be e over b. E over b, that's this line right here. And then the second line, let me do another color, would look something like, I don't know if it's going to be above or below that line, but it's going to be parallel. It'll look something like this. It'll look something like that, and that line's y-intercept, so that's this line. That line's y-intercept is going to be f over y. So if e over b and f over y are different terms, but these both lines have the same equation, they're going to be parallel, and they'll never intersect. So there actually would be no solution if someone told you, well, just the traditional way that you've done it, either through substitution or through adding, subtracting the linear equations. You wouldn't be able to find a solution where these two intersect if a over b is equal to c over d. So one way to view the singular matrix is that you have parallel lines. But then you might say, hey, Sal, but these two lines would intersect if e over b equaled f over y. If this and this were the same, then these would actually be the identical lines. And not only would they intersect in an infinite number of places. But still, you would have no unique solution. You would have no one solution to this equation. It would be true at all values of x and y. So you can kind of view it when you apply the matrices to this problem. The matrix is singular if the two lines that are being represented are either parallel or they are the exact same line. They're parallel and not intersecting at all, or they're the exact same line and they intersect in an infinite at an infinite number of points. And so it kind of makes sense that the A inverse wasn't defined. So let's think about this in the context of the linear combinations of vectors. That's not what I wanted to use to erase it. So when we think of this problem in terms of linear combination of vectors, we can think of it like this. This is the same thing as the vector AC times x plus the vector BD times y is equal to the vector EF. So let's think about it a little bit. We're saying, is there some combination of the vector AC and the vector BD that equals the vector EF? But we just said that if we have no inverse here, we know that because the determinant is 0, and if the determinant is 0, then we know in this situation that A over C must equal B over D. So A over C is equal to B over D. So what does that tell us? Well, it essentially tells us that, well, let me draw it. And maybe numbers would be more helpful here, but I think you'll get the intuition. I'll just draw the first quadrant. I'll just assume both vectors are in the first quadrant. Let me draw. So the vector AC, let's say that this is A. Let me do it in a different color. So I'm going to draw the vector AC. So if this is A, and this is C, then the vector AC looks something like that. Let me draw. I want to make this neat. The vector AC is like that. And then we have the arrow. And what would the vector BD look like? What does the vector BD look like? Well, the vector BD, well, unless I could draw it arbitrarily someplace, but we're assuming that there's no derivative. There's no determinant. Have I been saying derivative the whole time? I hope not. Well, we're assuming that there's no determinant to this matrix. So if there's no determinant, we know that A over C is equal to B over D. Or another way you could view it is that C over A is equal to D over B. But what that tells you is that both of these vectors kind of have the same slope. So if they both start at point 0, they're going to go in the same direction. They might have a different magnitude, but they're going to go in the same direction. So if this is point B, and this is point D, vector BD is going to be here. And you might just want to think, if that's not obvious to you, think a little bit about why these two vectors, if this is true, are going to point in the same direction. So that vector is going to essentially overlap, is going to have the same direction as this vector, but it's just going to have a different magnitude. It might have the same magnitude. So my question to you is, vector EF, we don't know where vector EF is. Well, let's say, I don't know, let me just pick some arbitrary point. Let's say that this is E, and this is F. So this is vector EF up there. Let me do it in a different color. Vector EF, let's say it's there. So my question to you is, if these two vectors are in the same direction, maybe of different magnitude, is there any way that you can add or subtract combinations of these two vectors to get to this vector? Well, no, you can scale these vectors and add them, and all you're going to do is kind of move along this line. You can get to any other vector that is a multiple of one of these vectors, but you can't get, because these are the exact same direction, you can't get to any vector that's in a different direction. So if this vector is in a different direction, there's no solution here. If this vector was, if it just happened to be in the same direction as this, then there would be a solution where you could, just scale those. Actually, there would be an infinite number of solutions in terms of x and y. And then, but if the vector is slightly different in terms of its direction, then there is no solution. There's no combination of this line, of this vector and this vector that can add you up to this one. And it's something for you to think about a little bit. It might be obvious to you, but the other way to think about it is when you're trying to take sums of vectors, any other vector, in order to move it in that direction, you have to have a little bit of one direction and a little bit of another direction to get to any other vector. And if both of your kind of ingredient vectors are the same direction, there's no way to get to a different one. Anyway, I'm probably just being circular in what I'm explaining. But that hopefully gives you a little bit of an intuition of, well, one, you now know what a singular matrix is. You know when you cannot find its inverse. You know that when the determinant is 0, you won't find an inverse. And hopefully, and this was the whole point of this video, you have an intuition of why that is. Because if you're looking at the vector problem, there's no way that you can find that there's no solution to finding a combination of the vectors that get you to that vector, or they're an infinite number. And the same thing is true of finding the intersection of two lines. They're either parallel or they're the same line if the determinant is 0. Anyway, I will see you in the next video.
Okay, so we went into a lot of vector stuff there at the end in the last couple of minutes of that. If you haven't studied vectors, don't worry about that part, but it's basically vectors have a direction and a distance, and they call it a magnitude. But the basic thing is, yeah, stop. There we go. The main points he's making is, when does a matrix not have an inverse. And I'll show you what I put in my notes here. So I was looking at this. The main thing to understand is to find the inverse, we take 1 over the determinant, and the determinant is A inside the lines there. Same thing, but that's what it is, times the revised matrix. If this is 0, we're multiplying times 1 over 0, which we know we cannot divide by 0. So when this, the AD minus BC, which is what we use to find the inverse, when that's 0, there is no inverse. So this would be 0 anytime that AD equals BC, right? Because we're subtracting BC from AD. If they're the same number when you multiply them together, it's going to equal 0, which means if A over B is the same as C over D in like fraction amounts, that means these would be equal to each other and again would be 0 or other combinations of that. If any of this is true, then the determinant is going to be 0 and we will have no inverse. No inverse. So really that's what this whole lesson is about, is when does it not have an inverse? It's when the determinant is equal to 0. Okay, so determine invertible matrices. That's what we need to do now. I click on that. Close a little half tab. All right, let's see. Answer 2 questions about the following matrix. Oh, so they're going to do it with how does the image of the unit with vectors here? How does the image of the unit square look under the transformation represented by the matrix? Choose what answer. So let's answer the second question first, because I think that would be easier, what we know, because we haven't really looked at vectors. So let's see, does the determinant equal 0? A times D, -5 times -3 is 15. Oh, I've got an announcement. Oh, you're listing all the department teachers of the year for BHS. So, by the way, our virtual teacher of the year is Mrs. Young. So if you have Mrs. Young, congratulate her. She is our virtual teacher of the year. And they're going through all the other departments in the building, BHS, over the announcements there. But let's look at the determinant. -5 times -3 is 15. And we subtract -1 times -7. Well, that would be a positive 7. 15 minus 7 is not 0. So this does have an inverse. So it does have an inverse. So looking at this, if it has an inverse, they would not have the same slope. So by process of elimination, knowing it has an inverse, I believe it is A, the way he was showing vectors. So if you miss this with the vector part of it, just screenshot that and turn that in. We'll give you credit for that. But that is correct. If it does not have an inverse, you will see this on vectors. So that helps with that. I didn't know it was asking that. They've added that since the last time I looked at this assignment. This means no inverse if they're all the same slope, because he was kind of explaining that. Next question. Oh, this one asks us, what is the determinant? And then, does it have an inverse? All right, so what is the determinant? Put that in the chat. What is the determinant of this matrix? So remember, it's AD minus BC. That's A, that's D. minus 2 times 3. So that is negative 70 minus 2 times 3. Minus 76. Right? So does it have an inverse? Yes. Only when that's 0 does it not have an inverse. Only when that's 0. So there you go. Negative 76 means it does have an inverse. Oh, let's see what this is. Okay. Consider the following matrix. If this was the coefficient matrix of a system of two equations, then it would look like this. The x has a coefficient of -1. The y has a coefficient of 3. The x of the second equation would have a coefficient of -4, and the y be 12. And it would equal some number, right? Some number. We could rewrite this in slope-intercept form. Y equals mx plus b, which, the b would be some number divided by 3. So since this has a slope of 1/3 and this has a slope of 1/3, how many solutions does it have? Pick number of solutions. Does it have one solution, or does it have 0 or an infinite number? Well, think about what that means. If they have the same slope, that means they could be like this with two different y-intercepts, right? Two different y-intercepts, which means there's no solution. The other possibility is that the second one is the exact same slope with the same y-intercept, which means there's an infinite number of solutions. But there's no way this has one solution if they have the same slope. So that means we want 0 or infinite. 0 or infinite. And that means the matrix does not have an inverse. Same slope means no inverse. No. So that should help you when you're doing these problems. No inverse. Perfect. All right, one last question. Oh, we have another one of these. So we need to find, once again, the inverse. 5 times 2 minus 10 times 1. Right? 5 times 2 minus 10 times 1. 10 minus 10. The inverse of this is 0. So we know it does not have an inverse, which means it has to be the same slope. See, this one of them has this slope and one of them has this slope, the green slope and the red slope. These are the same slope, which means that would be no inverse. So that's how that works. All right, I need a screenshot. Oh, I have to get down here. It's trying to push me off the page. 4 to 4. Close that. 4 to 4. Okay. Let's look to see what the quiz looks like, and we'll be done. We've done all of this now. Quiz 3 is this week. So many questions there are. What is the image we obtain when we perform the transition A on preimage B? That means you're multiplying. What do you get when you multiply? This times this. This is a 3 by 3. This is a 3 by 1. So you can multiply them and you end up with a 3 by 1, which is right here. What is the determinant? We were just doing that. Does matrix A have an inverse? Yes or no, and why? What is the inverse of this one? And then you may end up with fractions. Look, if it's a fraction, type it as a decimal. Put in your calculator, get the decimal form, and put it in there. If it ends up a fraction, and I haven't calculated it, so I don't know if that's a fraction or not. So that's important. If you put it as a fraction, it'll count it wrong, even if it's right, because it has a hard time with that. If that happens, email me and I'll go and look at it to see if it's right. But put it in decimal form, please. Point B is at 1, 1 on a graph. This graph is transformed using matrix A. What is point B located after transformation? So you want to multiply this by a matrix that is 1, 1. It's a 2 by 1 matrix with the points 1, 1. If you multiply this by the points 1, 1, what do you end up with? So you're multiplying it times, a matrix has 2 1s. That's what you multiply it by. And a 2 by 2 times a 2 by 1 gives you a 2 and a 1, where the x is the top and the y is the bottom. So when it wants to know the x and the y, it's talking about the top and the bottom numbers in your answer. Goes there. And that's it. 5 questions. 5 questions. A little interesting when you get into the inverses and all this, kind of getting to dealing with the fractions and the determinant and all that kind of stuff. Again, I don't think it's hard. It's just you really got to pay attention to the details or you'll get lost in there. But you guys are doing great with the matrix unit, so I'm not really worried about you. But if you're having any trouble, come see me Thursday. I'll have class open, even though nobody's required to be here in RTI. Good job, everyone. I'll be in class if you need help with this. So otherwise, if I don't see you again, enjoy your spring break. You've got the rest of the class to get a lot of this done and see how far you can get along there. So have a good spring break. We'll see you guys.
Bye.